Okay, so hi everyone. Today I will be explaining my solutions to the AD problems from today Codeforces Round. Yeah, I will be doing this, not Cheyenne. So, yeah. And uh, we won't be talking about problem because I didn't manage to solve it. And yeah, I'm also a little bit sad because after today contest I will be like 2 points away from master. So yeah, if I sound a little bit sad, sorry for that. And my first question is, does everyone hear me? Can everyone hear me? So once again, can someone write on chat, I hear you? Uh, so do you hear me? Yeah, I think you hear me. You should hear me. So we'll be talking through problems. Somebody asked on chat, is Div 2 usually this hard? I would say, I don't know. I think this one was normally hard, I think. Yeah, I think the problems wasn't normally they were well, I think difficulty of problems was normal, nothing exceptional. So let's talk about problems. Yes. So, in first problem, we are given some grid, and we want to cover this grid with horizontal and vertical dominoes. I call it dominoes, but they call it bricks. So we want to cover it with bricks, and brick is a piece of grid, a rectangle on this grid of size. It's such rectangle on this grid. It's a rectangle on this grid such that one of its sides is equal to 1 and the other side is at least 2, the length of the other side. So we want to cover it with bricks, but we want to cover it with bricks such that the difference between the number of horizontal bricks and the number of vertical bricks is as large as possible. So, does everyone understand the problem? Okay. So now to solution. It's problem A. So one of the things you have to keep in mind while solving problem A is that when you have some idea and it's not entirely stupid, it will probably work. So when doing problem A, you probably doesn't have to prove your solution. So first thing that we can notice is that when width of our rectangle or grid is even, so let's say 6, then we could just cover it all with vertical blocks of size 2. And then if we could cover it with vertical bricks of size 2, then our answer would be n times m divided by 2, right? And we know that if m is even, then we see that it's best solution that we can get, because we doesn't get any penalty for vertical bricks, and we get as much horizontal bricks as we can. So, but what if our m, or width of the brick, is odd? Then what we do, we are reducing, let's say that we have like this additional column here, right? So our width of the board is odd. So what we'll be doing, we'll be just replacing all the last bricks with bricks that are one unit wider, you know. So if our m is odd, then our answer will be n multiplied by m minus 3 divided by 2 plus 1. So this formula is just how many bricks we can set in every row multiplied by the number of rows, right? So does anyone have any questions for problem A? Okay, it was problem A, so it was quite predictable that nobody has any questions. So let's go straight to the problem B. I have to say that it was really funny problem. So let's go through the solution of problem B. So in this problem we have two permutations. Let's write the permutations from the one of the sample tests. So in this problem we have two permutations, permutation A and permutation B. And in one operation we can take two indexes. Let's say we take first index and fourth index. And what we can do is we can swap numbers in A on those indexes and numbers in B on those indexes. So after this swap we would get permutations like this, right? Because 1 and 4 was swapped in A, and in B we swapped 5 and 2. So our goal is to make such swaps, rearrange elements in A and B, such that after all these swaps, total number of inversions, we count inversions in A and then we count inversions in B, we sum them, and we want this number to be as small as possible. So in this example, it would be most sufficient. In this example, it would be most. I'm sorry. In this example, it would be most sufficient to get the permutation like this. As you see, the elements. As you see, these elements in A and B are like connected to each other. In the start, 2 and 4 was on the same index, and here it's the same. So Maybe I will say what inversions are if someone don't know this. So, for example, 5-4 is inversion, cause in sorted permutation they should be in different order. Right? So, inversion is the pair of indexes such that they are like ordered badly. So what's the solution? When I was thinking about this, my first idea was to look at this like as pairs. So we have 3-3, pair 3-3, pair 2-4, pair 5-1, pair 1-5, and pair 4-2. And what we are doing in one operation is taking two of those pairs and swapping them, right? So yeah, and then we are just counting inversions on first positions and then inversions on second positions. So now what we could do is just create another permutation. So how we would create this permutation? I would create it as follows. When we see that we have pair 3-3, we would say that this is our index in our new permutation and this is our value. So I know that in our new permutation P, on the third position I will have 3. On the second position I will have 4. On the fifth position I will have 1. On the first position I will have 5. And on the fourth position I will have 2. So now I see that in this starting when I will look at the function of the cost in this starting permutation, it will be just the number of inversion. So now I want to think how this number of inversions would change if I would swap two elements in this permutation. So I can prove that after I swap these two elements in these permutations, my number of inversion will grow by 1, cause elements in these permutations are sorted by the first index, so no permutation in no inversions in A. So after I swap two elements, I get new inversions. After I swap two adjacent elements, I get one additional inversion in A. And possibly I subtract at most one inversion in B. Right? Does everyone agree? So now the most beautiful observation. It's always sufficient to just have the permutation A sorted. Why? Because as we see, swapping two adjacent elements never helps us. Right? So when swapping two adjacent elements never helps us, it's never optimal to swap two elements. It's always optimal to leave this permutation as it's on the start. Right? So that's what we'll write on the output. We'll just wrote the sorted A permutation and then the elements in B as they are connected to elements in A. Right? So in this example, we would have sorted A permutation, and in permutation B we would have 3 on third position, 4 on second position, 1 on 1 on 5th position, 5 on 1st position, and 2 on 4th position. So, does anybody have any questions? Yeah, so now to a little bit more interesting tasks. So in problem C, we are given three numbers, A, B, and R, and what we want to do is we want to find the such x. We want to find x such that this value is as small as possible, right? The absolute difference between a XORed with x and b XORed with x is as small as possible, and x doesn't exceed r. So I hope everyone understands this. So now to the solution. In this problem there is one key observation. As I saw on chat, some people were wondering if it's some formula or something. No, it's not a formula, it's just one observation and then some greedy. So there is one observation, or maybe two observations. First observation is, when we look, of course when we have XOR we want to look at the binary representation of A and B. So let's say that A is 0, 0, 1, 0, 1, 0, and B is 1, 0, 0, 0, 1, and 0. So the observation is the observation is, when we have two ones on the same position, I claim that no matter what x we choose, there will when A and B are same on such when A and B are having the same value on some position, then no matter which x I choose, they will always stay the same. Because if I have two ones and I give x 0 on this position, then it will stay, right? It will be still two ones. But if I give x 1 on this position, then after my XORing there will be two zeros on this position. So when two values in A and B are the same, they will stay the same after XORing. And it's the same for when they are different. When they are different, they will stay different after XORing. So the solution goes as follows. When A and B are the same, we are just, our answer is equal to 0, right? Because, well, it's the best possible answer and we can always get it by XORing with 0. But what happens when A is smaller than B? We can assume that A is smaller than B. If A is bigger than B, then we just swap them. So, if the A is smaller than B, let us look at the first position such that A is different than B. So we know that at this position B will be 1 and A will be 0, because that's just how being smaller works. So let me write some example. And then there is one beautiful observation. In perfect world, if A and B would be different on every position, then our perfect solution in this would be B would be power of 2 and A would be power of 2 minus 1. A would be power of 2 minus 1. So I claim that we never want to touch this first bit of B. Why? Because if we would touch it, we would make A bigger by the same amount as B. And also, if we can touch it, if we can set our X on 1 here, if we can set X on 1 here, then they are like just swapping places. So if we can say that X will have this bit set on to 1, then X can also have all those bits set as it wants. Right? Because I know that the sum of all bits over here is smaller than this bit. Because that's just how binary representation works. So, right now to the solution. As I now showed, we can leave the first bit untouched, right? The first different bit. So what are we doing then? We are just doing simple greedy. We are just doing simple greedy. Yeah. So we are just doing simple greedy, right? So what we are doing? I know that after leaving the first bit untouched, the A and the B will always be greater than A. No matter what I will do, like after the first bit, B will always stay bigger than A, right? Because in the situation where A is biggest, A is still one smaller than B, right? So what we'll be doing? I know that B is greater than A. It's a really useful information for me. Because after I go further, what I'm doing? When I see 0 and 1, so A is greater on this bit than B, I'm not doing anything. Because it's good for me. The thing I want to do is just make A as big as possible and B as small as possible. But when I see 1 and 0, then I can do something. I can say that our X, so our XORing value, will be set on 1 on this. Right? I can do it greedily. Because now our A is getting bigger and our B is getting smaller. So I am just setting X to 1. So it's almost a solution. But right now, we also see that our X can be too big. Because we also have the value R. So we are just setting X to 1 when we can. Right? So if our X would get too big after setting to 1, we are just leaving it. We are just setting X to 0 and we say, okay, maybe somewhere in the future, we could set it to 1 and get ourselves a better result. Right? So, does anyone have any questions? I'm really sorry for my speaking today, but it's my first time and I'm a little bit stressed, so have a little mercy for me. With every other time, if there will be. Yeah. So does anyone have any questions? I can also repeat if someone wants any part. Yes, the stream will be saved and also thanks bro. Okay, so there are questions to repeat, so I will try to, make everything easier. So let's try once again. The first observation is as follows. Let's assume that B is greater than A, because we can just assume it. If A is smaller than B, we will just swap them. So, okay, maybe I will write on keyboard because there are many complainings on my... Let's assume that B is greater than A. If B is smaller than A, then we can just swap them. So now, let's look on the binary representations of both of them. So let's say that A is 0, 1, 0, 1, 1. And let's say that B is 1, 0, 0, 1, 0. Right? So my observation goes as follows. And it's the most, it's the most important claim in this task. The most important claim in this task goes as follows. I claim that we will never have to move the first bit, right? So I say that we will never have to move the first different bit, right? Because we also have this observation before that we can just skip the bits that are the same. Because if A and B are the same on some bit, then they will stay the same after XORing. It's one of the most basic most basic properties of XOR. So now let's only look at the values when they are different, right? So 0, 1, 1, 0, and 1, 0. So I say that we will never need to do operation on the first bit, right? How do you prove it? I say that if I can do the operation on the first bit, right? If I can set x to 1 on the first bit, then I can set x to any other value on the any other bit, right? How do you prove it? It's really easy to prove. Because if I would set x to 1 on this value, then x would be equal to some 2 to the power of k, right? When the k is the number of this bit. And if I would set, and I know that any number that is composed of the bits that it's composed of the bits from 0 to k minus 1 is smaller than 2 to k. So if I can set x to 1 on this bit, then I can set it to any other value on any other bit. So now I know that I never need to move the first bit. So also now I have the most important information in the whole task. I know that B is always greater than A after the operations. So now I will just do greedy to make A as big as possible, right? It's my only goal now. So what I will do, I will go from the bits from the most important to the least important bits. And when I am on some bit such that they are different, what I am doing is checking if I can set x to 1 on this bit, right? If I am keeping the track of my actual x, and when I'm setting x to the 1, I know that I will add some 2 to the power of k to my x. And I am checking if after this adding, x plus 2 to the power of k is like still smaller than r, right? So if x plus 2 to the power of k is still smaller than r, then it's great. I'm just setting x to 1 on this bit and I am XORing both of these values with 2 to the power of k. But if I can't do this, then I am just skipping this bit and going to the next one. So, yeah. I'm really sorry if it's over someone's head. I am trying. But you can always read the editorial, or, you know, uh, re just, you know, I you can just rewatch this video, maybe then you will understand, or, you know, read the editorial. But I can also answer one of your questions if you have any specific, if anyone have any specific questions. Yeah, okay, so now we'll go to D. So I think D is the most standard of all these problems. It's really just use some techniques. But as you see, it appears on Codeforces. Not only ad hocs are on Codeforces, there are sometimes problems like this. So, okay. Let me explain this statement to you. The statement goes as follows. We have some array. Let's say array. I will not handwrite because I know that some people don't like my handwriting. And what we want to do is choose some subset of the elements of this array, right? So let's say we choose subset like this. And when I choose some subset, I calculate my result as follows. I am taking maximum of the sum of the elements that I have taken, right? So here my sum would be 1 plus 5 plus 3. And also maximum of all the sums of intervals that I have not taken. So here those intervals would be 4, and the second interval would be, wait, I'm sorry for non-coloring. So here one interval would be 4, and the second interval would be 3 too. So I'm just taking the maximum of this sum, so 1 plus 5 plus 3, and the maximum of those two values, so maximum of 1 plus 5 plus 3, of 4, and 3 plus 2. Right, so does anybody have any questions to the statement? Yeah, okay, I don't see any questions. So the key idea here is that we'll be binary searching over our answer, right? Because when we binary search over our answer, what we are getting is we know which intervals we can take, right? When we want to check if we can get the answer smaller than our x, or smaller, doesn't exceeding our x, when we have this information, we know which of the intervals are good, right? We can take all the intervals that are good. So now we'll be just doing simple DP. So let me write. DP from the index E will be the smallest sum of the black elements, or the blocked elements as they call them, elements that we can get, assuming that E is blocked. of the block elements on prefix blocks elements, the smallest sum of the blocked elements on prefix that we can get assuming that I is blocked. So how to calculate this dp? Well, we see that when we are in some I, some suffix of this prefix will be good. So we are considering how long can this last non-blocked interval can be, right? So we can do it, I don't know, by just some simple 2 pointers, or yeah. If we know that for this element the longest such interval was like this, right? The longest interval such that we can take it in our bin search, because we have this information from bin search how big the sum of our interval can be. So if we have this sum, if we know how long the interval can be for our predecessor, we can just, you know, we can just shorten it naively, right? Because we can just shorten it naively because it will be amortized. So when we know that we want to check so we know that dp from I would just be the A from I plus minimum over all dp's here, right? And this minimum we can make just on segment 3. So does anyone have any questions? You could also implement it on priority queue if someone prefers. The most crucial idea here was to use bin search. We are on problem D. Yeah. So, repeating, we are doing bin search because if we see maximum over some intervals, we are just doing bin search, right? Because now when we do bin search, we know for each interval if it's good or not, right? We know that the intervals that are good are the intervals not exceeding x. Then we are just doing simple dynamic programming, right? So here is the definition of dynamic programming, and as we see in this dynamic programming, the smallest sum of the blocked elements on the prefix that we can get assuming that I is blocked, we see that we can, the last non-blocked interval can be the last blocked element. We have I, our newest blocked element, and we are thinking which element was blocked before, right? So we know that the elements that we can block will be some connected interval of the elements, right? Our last non-blocked interval can be the longest. Yeah, I'm sorry for this confusion. Maybe I will try to tell it once again about this. Because like the last interval that could be unblocked, right? Because we have I, then some unblocked interval, and then we have J, right? Our last blocked element. So I say that this interval here, let's call it S, sum of S must be smaller than our X in binary search, right? Because if it would be greater, then our maximum would be too big. So if somewhat else must be smaller than x, or not exceeding x, then we can just find, I don't know, with another bin search or with some amortization, we can find the longest such s, and then I know that any shorter s will have just smaller sum, right? So any shorter s will be good too. So yeah, so my dp can take from any dp such that this dp lies in the longest s. So do you understand? Okay, so thank you for discussing these tasks. And yeah, sorry for my bad English and me stressing out. So see you next time, I guess. And bye. Thanks and bye.